Welcome back to our series on mathematical statistics. I'm Mark Ledbetter. This is lecture 14. We are in video 29 and we are going to do part 7, the final portion of sufficient statistics. So last time we introduced or extended sufficient statistics to multiple parameters, and then we went over the very famous and important Rao-Blackwell theorem and did an example. And the example we did, we showed that z equals n minus 1 s squared is independent of y equals x bar when x sub I has a normal distribution with mean mu and variance sigma squared. Okay? And so we were able to show that z was independent of y. Okay? And so that's what this first page is, where we did that proof. So let's do another example. In this video, we're going to do another example of the Rao-Blackwell theorem and multiple parameters, and then we're going to go over some supplementary information that was not in the textbook but would be in a graduate level course. And so the addition of the supplemental information really makes this much more difficult topic, I think, not because it's hard, it's just because there's so much information and so many implications to keep straight. So I'm hoping that giving you exposure to this, if you go to grad school, will help you handle that better than I did the first time. I mean, I made an A and did well, but I struggled. I could have done a lot better if I had seen the material before. Okay. So here's our example, number 6 for this section. x1 to xn is a random sample from a gamma distribution with a known value of alpha. So this is not a parameter. So this is not a multiple parameter example. This is going to be the Rao-Blackwell, I believe. And an unknown value of theta greater than 0. And you could say beta here if you want. Theta equals beta, which is greater than 0. Okay, I believe our PDF we write as f of x alpha beta equals 1 over gamma alpha beta to the alpha, or did we use, we did use theta, didn't we? Okay, so I get my textbooks mixed up, so I guess it's 1 over, so it's theta equals 1 over gamma alpha theta to the alpha x to the alpha minus 1 e to the negative x over theta, where x is greater than 0, theta is greater than 0, alpha is greater than 0. Okay, so we don't use beta in this textbook. Okay, another textbook. Okay, so that's our PMF, or PDF. It's continuous, PDF. And we want to know, is x sub I of the exponential family? And we need to show this by writing the PDF. Then B, we're going to find a sufficient statistic of theta. So let's do part A here. So we have f of x sub I theta is equal to, in the denominator, gamma of alpha, which is a constant, theta to the alpha, 1 over x to the alpha minus 1, e to the negative x over theta, and I need to put sub I here, and if I want to put it sub I, x sub I over theta negative, x greater than 0, theta greater than 0. Okay, so I can rewrite this as an exponent, so I'm going to have, let's see, exp. The first term, I need this as e to the log of this, so log of 1 over gamma alpha theta to the alpha. And so this is going to be log 1, which is 0, minus log of gamma of alpha, theta of alpha. This is a product, so that's going to be negative log of gamma of alpha minus because there's a minus out here. So if I put a parentheses here, it'll be plus log of theta alpha, but that's going to be negative log of gamma alpha minus log of theta to the alpha, and I can pull this down in front. So this is going to be negative log of gamma alpha minus alpha log theta, and then I'm going to have plus alpha minus 1 x, let's see, log x sub I. And so that was this term. Let me erase here quickly. I hope that if I go too fast for you, stop the video and write down and see, do it for yourself and make sure. So this is becoming e of log of x sub I to the alpha minus 1. So this exponent part becomes alpha minus 1 times log of x sub I. And then we already have this in the exponent of e, so we don't have to change that portion at all. Okay? And so we have minus x sub I over theta. Minus x sub I over theta. Okay. And so now we have that. And what we want to do is rearrange this. So this is equal to exp of, and I'm going to put negative log of gamma of alpha. And let's see, so, oh yes, and then plus, remember alpha is a constant. So then plus alpha minus 1 log of x sub I. And then I have minus alpha log theta minus x sub I times 1 over theta. Okay. Now this is s sub x. This is q sub theta, and this is k of x times p of theta. And remember that the sufficient statistic is the sum of k of x. That's the sufficient statistic. So, so we can find that, but that's part B, I believe, or the next, let's see. So we just want to know, is it an exponential family? And the answer is, therefore, yes. F of x sub I theta is in the exponential family of distributions. Okay, by the theorem. And we don't have a name for that by the, oh, okay, so therefore I'm going to change this so I don't have to rewrite all that. I've left a space and I'm going to leave that. I'm saying, therefore, by the exponential family of distributions theorem, yes, f of x of I theta is in the exponential family of distributions. Okay, now, I can do part B. So part B is find a sufficient statistic of theta. So the easy thing is you can use the factorization theorem here, but I'm not going to because I already have it written as an exponential family of distributions. By the theorem for the exponential family of distributions, the sufficient statistic. You could say a sufficient statistic if you prefer. That's more accurate, actually. A sufficient statistic for theta is y equals sum of k sub x of x, which is equal to the sum of x sub I. Okay? You could do this by the factorization theorem and rewriting this if you wanted to. I'll leave that for you to do. You should be able to do that by now. Okay, so part C is we want to let z equal the sum of ai xi divided by the sum of xi, where not all the constants a1, a2, an are equal. Okay? Some can be, it could be that all of them are equal except one, but we're saying that not all of them are the same. Otherwise, we could just factor the a sub I out of the, we could just factor out the a sub i's. If they're a constant, they don't change, then you could rewrite this as a sum of xi over sum of xi, which is just equal to a. So we're saying that's not the case here. Okay? Z is not equal to a constant. It's equal to linear combination of the x's divided by the sum of the x's. Okay? We want to show that z is independent of y equals sum of xi. So we're going to do this the same way. We're going to use the MGF. We will use the MGF. And so e of e to the tz is equal to negative infinity. Actually, let's see. So this is just going to go from 0 to positive infinity. We could put negative infinity, but there's no reason to do so. 0 to infinity, 0 to infinity, dot, 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 0 to infinity of exp of t times z. So this is going to be t, and then z is the sum of ai xi over the sum of xi. And then we have the distribution. So we're going to have the PDF, the joint PDF of this. So let me do the joint. I realize I'm skipping steps here by doing this. The book assumes that you already know how to do this, and I know that you know how to do this, but it's good practice for us to go through this. Make sure that you get the algebra right. So the joint PDF of x1 to xn equals the product of f of xi theta I equals 1 to n equals the product of 1 over gamma of alpha, theta to the alpha, x sub I e to the negative x sub I over theta. And this can be rewritten as the product of gamma of alpha to the negative 1 and theta to the negative alpha. And then I have x sub I e to the negative x sub I over theta. And so this product is equal to gamma of alpha to the negative n, theta to the negative n alpha. Okay, because we have theta to the negative alpha times theta to the negative alpha, theta to the negative alpha. There's n of these, so it's going to be theta to the negative alpha plus alpha plus alpha. There's n of those, so it's going to be theta to the negative n times alpha. Okay, so this is stuff you'll have to know for the test. You'll have to be able to do this. Oops. Okay, and then we have the product of x sub I. There's nothing we can do with this right now unless we do exp and then log. Then we can change it to a summation. And then we have e to the negative sum of xi over theta. Okay, so this PDF, joint PDF, is what we're going to put next, because that is e e of e to the tz is going to be e to the tz times f of z, or f of x, so so of f of x sub I, f of x of 1 to n, okay? And so we're going to write gamma of alpha to the negative n, and I'm going to use some brackets to make sure that's clear. Theta to the negative n alpha, the product of x of I, and then e to the negative sum of xi over theta, dx1, dx2, dxn. So, clean up down here. And so we're going to now do a substitution. So let wi equal x sub I over theta. So then dwi will be 1 over theta, it's a constant, dx sub I, and this implies that dx sub I is equal to theta times dwi, okay? And so x sub I, so here we're going to solve for x sub I. So we have this that we need, and then we're going to say, that's a semicolon, or supposed to be, x sub I equals theta times w sub I, and that implies sum of x sub I equals theta sum of w sub I. So we'll need this as well. Okay? And then a times x sub I is going to be ai times theta w sub I. We just used this expression here and multiply both sides by a sub I. And I missed my sub I there. A sub I, x sub I is equal to a sub I times theta w sub I. And this implies that the sum of a sub I, x sub I equals theta sum of a sub I, w sub I. Why am I doing that? Look at this term here. I need the sum of a sub I, x sub I. And on the bottom, I needed the sum of x sub I. So I now have the sum of x sub I here, and I also have the sum of a sub I, x sub I here, that substitution. Okay? Now, I can also use this here to say that x1, x2, up to xn, this is the product of x sub I, is equal to, I'm going to take this for each one. I'll have theta times w1, theta times w2, up to theta times w sub n, which is going to be theta to the n, w 1 times, so this is going to equal, actually, let me write this a little more compactly. So I have product x sub I equals x sub 1 up to x sub n multiplied equals theta to the n, w1, w2, up to wn, the product. Okay? And so we need this quantity as well. Now, if x sub I is equal to 0, okay, this implies that w sub I, which is right here, is equal to 0. And x sub I equals positive infinity implies w sub I is equal to positive infinity. Again, using this substitution, you plug in infinity. Infinity divided by theta is still infinity. So we have our And remember that theta is greater than 0. Okay? Then e of e to the tz is equal to 0 to infinity times integral 0 to infinity ... 0 to infinity for the nth version. And then I have exp to the t theta sum of ai wi over theta sum of wi. These cancel. Okay? And then I have gamma of alpha to the negative n, theta to the negative n times alpha. And then I have theta to the n, w1, w2 up to wn, raised to the, that's x sub I product, raised to the alpha, not alpha I, alpha minus 1, whoops, wrong thing, alpha minus 1, e to the negative theta sum of wi divided by theta. So again, this theta and this theta is going to cancel. And then I have theta to the n, dw1 up to dwn. Okay? And this is equal to the multiple integral from 0 to infinity, okay, of exp to the t times sum of ai wi over sum of wi. And then I'll have gamma of alpha to the negative n. I'll have theta to the negative n alpha. And then, so that's this. And then I will have theta to the n times theta to the n times alpha minus 1. So theta to the n, alpha minus 1, and then theta to the n. This is going to be n alpha minus n, theta to the n alpha minus n, theta to the n, which is equal to theta to the n alpha minus n plus n. So those cancel, is theta to the n alpha. And so I have theta to the n alpha and then I have w1, w2 up to wn to the alpha minus 1, e to the negative sum of wi, and then I have dw1, dw2 up to dwn. Now, these cancel because I have theta to the negative n alpha, theta to the n alpha equals theta to the negative n alpha plus n alpha equals theta to the 0 equals 1. Okay, so these have canceled. And so this is equal to 0 to infinity, 0 to infinity, ... 0 to infinity, exp to the t sum of ai wi over sum of wi, gamma of alpha to the negative n, w1 times w2 times ... wn to the alpha minus 1 e to the negative w sub I dw1 dw2 ... dwn, okay, which is independent of theta. Okay, so we have shown, part C, we have shown that z is independent of y equals sum of x. Okay, so we've shown that this is independent of theta, and therefore z is independent of y, the sum of xi. Okay, using the MGF. All right. Now, so let's see, that's 7. Okay, so that's the end of that. Now, we're going to talk about the supplemental information. This was not covered in the textbook, and it won't be on the test. But I want to, again, if you're going to grad school, please continue to watch the video. A minimal sufficient statistic. And our textbook really mixes up what it says about sufficient statistics when it really means minimal sufficient statistics and complete sufficient statistics. And those are different things. So anyway, let's look at this. So we have the definition of a minimal sufficient statistic. A sufficient statistic y is equal to u of x1 to xn is a minimal sufficient statistic if for any other sufficient statistic z equals u2, a different function of x1 to xn, y is a function of z. Okay? So y equals f of z, let's say, for all z that are sufficient statistics. Okay? So, now, that's the definition. So, it's often very difficult to do so. So, we're going to come up with a theorem. How to determine if y is a minimal sufficient statistic. Let f of x theta be the PMF or PDF of a sample x of 1 to x of n. Suppose there exists a function y equals u of x of 1 up to x of n, such that for any x, so any actual observed values of x, x1, x2 up to xn, and x prime, a different sample, observed sample, then the ratio of f of x theta divided by f of x prime and theta does not depend on theta. Okay, so if this is true if and only if y of x equals y of x prime, if this condition has to be true. Okay, so the ratio does not depend on theta if and only if the function of x, y of x, is equal to the function of x prime. Then y of x, which is u of x1 up to xn, is a minimal sufficient statistic for theta. Okay, so I trust you can see that this is not crystal clear on how you do it. Until you see some examples, this won't make a whole lot of sense. I'm not going to do an example, I don't think. I don't remember. Let's see. No, we're not going to do an example. So there are textbooks out there like Casella and Berger where they do some examples of this. And if you're interested, by all means, look those up. Okay. So, but the ratio here has to be independent of theta if and only if the statistic on sample x is the same value as on x prime. That's the only way that can happen. If that's true, then u of x1 to xn is a minimal sufficient statistic for theta. All right. So I know it's a little hard to get your mind around if you haven't seen this before. Now, an ancillary statistic. A statistic s of x equals, let's say, a function v of x1 to xn, whose distribution does not depend on theta, is called an ancillary statistic for theta, or an ancillary. I call it ancillary. Ancillary might be another way to say it, so I have trouble with both. So a statistic s of x, which is a function of the sample, the random sample, whose distribution does not depend on theta, the distribution, okay, not the statistic, but the distribution of the statistic. If it doesn't depend on theta, then it is a ancillary statistic for theta. Okay. Now we come to the definition of a complete sufficient statistic or complete sufficient statistic. I left out a word. Let f of y and theta be a family of PMFs or PDFs for a statistic. A family, not just one, but a family. Okay, so yeah, so that means that theta may be theta equals theta 1 up to theta p, let's say. Okay. It's a family of PMF or PDFs for a statistic y of x equals u of x1 to xn. This family of probability distributions, the family is called, so the family is called complete, okay, if the expected value with respect to theta of g of y equals 0 for all theta, if that implies that g of y is 0 almost everywhere, so almost always, then y of x is called a complete statistic for theta. This is real simple, isn't it? No, it's not. Okay, I was being sarcastic. It's not so simple. So let's see if we can look at this again. So we have this PMF or PDF that's a family of distributions. It's family because because theta can take different values. Theta is in sigma. So it can take different values. So each time it's a different value, it's a different PMF or PDF, right? I mean, it takes a different function. So it's a family of functions or distributions. Okay. So this statistic is operating on the random sample. So this family of probability distributions is called complete if the expected value with respect to theta, okay, not with respect to x, but with respect to theta of g of y is equal to 0 for all theta, if this is only equal to 0 for all theta if g of y is equal to 0 for almost all cases, okay? Then y of x is called a complete statistic for theta. So completeness is a property of a family of distributions, not a particular distribution, okay? Now we'll talk about Basso's theorem. It says y of x equals u of x1 up to xn is a complete and minimal statistic. If it is, then y is independent of every ancillary statistic. Okay, so this is good to know. If you can prove that y is a complete and minimal statistic, then you know that it's independent of every ancillary statistic. Okay. Again, I hope you can see by adding these other theorems and definitions, we're making this much more complex than what we've covered so far. Okay. Another theorem, let x1 to xn be IID observations from an exponential family. Then the joint PMF or PDF is of the form h of x1 to xn, c of theta 1 to theta p, exp, okay, of the sum of wj of, so wj is a function of theta 1 to theta p times t sub j of another function of x sub 1 to x sub n, okay? Where theta 1 up to theta p are unknown parameters, then y of x equals the sum of t1 xi and the sum of t2 xi up to the sum of t sub p of, got too many of them, xi. Actually, I should scratch out this one. This statistic, the sum of t1 xi, sum of t2, function t2 xi, up to the sum of this group, this vector of these, is a minimal, sufficient, and complete statistic if the parameter space has an open set in R sub p. Okay? In other words, you can find an open set in R sub p. I'm not going to get into that, but that's actually not too hard when you have an example in front of you, but it's also not easy to conceptualize. And then finally, there's a theorem that says if a minimal sufficient statistic exists, then any complete statistic is also a minimal sufficient statistic. So if you can show that a minimal statistic exists and you can find a complete statistic, then you know that that complete statistic is also a minimal sufficient statistic. And that's handy at times too. Okay, so I hope I haven't confused you too much with that supplementary information, but I wanted to give you a overview of what we did not cover and what you will cover in graduate school if you go to graduate school on this topic. All right, please, if you have questions, please come to virtual office hours. If you need help with a problem prior to coming to office hours, then by all means email me, but email me a picture of the problem and a picture of your work so far so I can help you wisely and be more helpful in my response to you. And you need to send me a picture of the problem because I may not have it available and it may take me a while to get it available, so then that will delay my response to you. So, and I will get back to you as soon as it's possible for me to do so. Please take care of yourself, stay safe, and we hope to see you next time.